Hello everyone. In this video, we will learn to define and explain what is meant by a polar covalent and a non-polar covalent bond. 2. Define, explain and apply the concept of electronegativity when considering the nature of a covalent bond. 3. Describe and explain the periodic trend of electronegativity. 4. Explain how the Pauling scale can be used to describe bond polarity. 5. Calculate a dipole moment and use appropriate diagrams to depict bond polarity. In the earlier videos, we discussed two different types of bonds, an ionic bond and a covalent bond. An ionic bond is formed when an electron is completely transferred from a metal atom to a non-metal atom. Since the metal atom loses an electron, it acquires a positive charge. That is, it becomes a cation. And because the non-metal atom gained an electron, it acquires a negative charge. That is, it becomes an anion. A covalent bond, on the other hand, is formed when two non-metal atoms share an electron pair equally between them. Each of the participating non-metal atoms donates an electron, and the electron pair formed is shared equally between the two atoms. Now, the word equally shared is very important here. The shared electron pair is exactly in between the two bonded atoms. That is, same distance from both the atoms. This type of bond is called as non-polar covalent bond. These two scenarios are theoretical extremes. In reality, no bond is either completely ionic or completely covalent. In reality, for most of the molecules, the electron pair between the bonded atoms is not exactly in the middle, but is more closer to one of the atoms than the other. Since the electron pair is more closer to one of the atoms, the atom that is closer to the electron pair acquires a small amount of negative charge. That is a partial negative charge. This partial negative charge is represented by delta minus sign on the atom. And the atom that is farther to the electron pair acquires a small amount of positive charge. That is a partial positive charge. And this is represented by writing delta plus sign on the atom. These partial charges on bonded atoms are referred to as poles, that is, positive and negative poles, and the bond is referred to as polar covalent bond. The polar covalent bond involves unequal sharing of electrons, that is, the shared electron pair is closer to one of the atoms. Now, what makes this shared electron pair in a bond move closer to one atom than the other? In this video, we will discuss the property that makes this shared electron pair to be closer to one of the participating atoms. This property is called as electronegativity. We will discuss more about this in the next slide. Electronegativity of an atom is defined as the ability of an atom in a molecule to attract the shared electron pair to itself. The properties that we discussed earlier, such as ionization energy and electron affinity, are measurable properties. However, electronegativity of an atom is not a measurable quantity. That is, we cannot measure the electronegativity of an atom by doing an experiment. The electronegativity of an atom is a relative property. That is, we define electronegativity of atoms relative to each other. In other words, these electronegativity values are not absolute. For example, let us consider a covalent bond between hydrogen and fluorine. The shared electron pair is closer to fluorine than that of hydrogen. Therefore, we can say the electronegativity of fluorine is greater relative to the hydrogen. And we can assign some arbitrary values to represent the difference in electronegativities between these two atoms. Of this unequal sharing of electrons, fluorine gets a partial negative charge and hydrogen gets a partial positive charge. This polar covalent bond can also be represented by drawing an arrow, while the head of the arrow should point towards the more electronegative element, that is fluorine, and the tail points towards the least electronegative element, that is hydrogen. If we place a sample of hydrogen fluoride molecules in an external electric field and turn on the electric field, the molecules in a hydrogen fluoride sample orients in such a way that the fluorine atoms, which are partially negative, orient themselves towards the positive pole and vice versa. Since the electronegativity values are not absolute, we use several different numerical scales to express the relative electronegativity values of various elements. The most widely used scale is called Pauling scale of electronegativity values. Linus Pauling, in the year 1922, assigned the electronegativity of all the elements in the periodic table relative to the fluorine atom. Let us now discuss how he assigned these electronegativity values. Let's take an example of hydrogen fluoride molecule. Linus Pauling reasoned that the HF bond energy should be a geometric mean of HH bond energy and FF bond energy. That is, HF bond energy expected is equal to the HH bond energy times the fluorine-fluorine bond energy raised to the power of half. So he measured the HH bond energy in an experiment and found out that it is 432 kilojoules per mole. Similarly, he measured the bond energy between two fluorine atoms, which is 159 kilojoules per mole. And he then calculated the geometric mean, which is 262 kilojoules per mole. This is the expected bond energy of hydrogen and fluorine. However, when he measured the HF bond energy, he found that it is 560 kilojoules per mole. This is much higher than the expected bond energy. The difference between these two values, delta, is equal to 560 minus 262, which is 298 kilojoules per mole. He attributed the difference between the expected and the observed bond energy to the difference in electronegativity values between hydrogen and fluorine atoms. He used the following formula: the electronegativity of fluorine minus the electronegativity of hydrogen is equal to 0.102 times square root of delta, where delta is HF bond energy observed minus HF bond energy expected. We already know the value of delta, and Linus Pauling assigned an arbitrary value of 4.0 as electronegativity of fluorine, and he then calculated the electronegativity of hydrogen. So this value is relative to that of fluorine. Let us now understand what this formula exactly means. According to Pauling, if the hydrogen and fluorine has same electronegativity, then the HF bond energy should be a geometric mean of HH and FF bond energies. However, because the electronegativity of fluorine is higher than that of hydrogen, the shared electron pair between the hydrogen and fluorine is more closer to fluorine atom. Therefore, fluorine atom acquires a partial negative charge and hydrogen acquires a partial positive charge. And the electrostatic force of attraction between these two opposite poles increases the bond strength. Therefore, it requires more energy than expected to break the HF bond. Linus Pauling then repeated the similar kind of experiments with all other elements and found their electronegativity values relative to the fluorine atom. We will discuss all these values in the next slide. This image shows the electronegativity values of all the elements in the periodic table calculated by Linus Pauling. If we closely observe the values, we can say that the electronegativity increases across a period from left to right and decreases down the group. The periodic trend of electronegativity is similar to that of electron affinity. The electronegativity values range from 0.7 for francium, which is at the bottom left of the periodic table, to 4.0 for fluorine atom, which is at the top right hand side of the periodic table. The difference in electronegativity values between the bonding atoms determines the type of bond between the two atoms. That is, the greater the electronegativity difference between two atoms, the greater is the polarity of the bond. For example, if we take a bond between any two identical atoms, such as chlorine bonded to another chlorine atom, the electronegativity difference value is 0. Therefore, the electron pair is equally shared between the two chlorine atoms and the bond is called nonpolar covalent bond. Second, if we take a bond between a metal atom and a non-metal atom, such as sodium bonded to chlorine, the electronegativity difference value will be high. Therefore, it is an ionic bond. If we take a bond between two different types of non-metal atoms, the electronegativity difference will be of intermediate value. Therefore, it will form a polar covalent bond. Let us do an example. Arrange the following bonds in the increasing order of polarity: sodium chlorine, cesium and fluorine, chlorine hydrogen, oxygen hydrogen, and hydrogen hydrogen. Pause the video here and try to answer this question. You can use the electronegativity values shown in the previous slides. Okay. First, we can calculate the electronegativity difference between the bonding atoms for each type of bond. For sodium and chlorine, the electronegativity difference is 2.1. For cesium and fluorine, it is 3.3. For chlorine and hydrogen, it is 0.9. For oxygen and hydrogen, it is 1.4. And for hydrogen and hydrogen, because they are identical atoms, the electronegativity difference is 0. We learned earlier that the smaller the difference in electronegativity between the two atoms, the smaller is the polarity of the bond. Therefore, the following is the increasing order of polarity. Hydrogen-hydrogen is the least polar bond, followed by chlorine-hydrogen, then oxygen-hydrogen, sodium and chlorine, cesium and fluorine. Next, we will discuss a concept called as dipole moment. Molecules that have positive and negative poles, that is, the polar molecules, are said to possess a property called as dipole moment. Dipole moment is represented by a Greek letter mu, and dipole moment mu is equal to Q times R, where Q is the magnitude of the partial charge on the atom and R is distance between the charges. The commonly used unit of dipole moment is dBi, and the SI unit of dipole moment is Coulomb meter, and the conversion unit that converts dBi into Coulomb meters is 1 dBi is equal to 3.336 times 10 to the negative 30 Coulomb meter. From the formula, we can say that the greater the electronegativity difference between the two atoms, the greater is the magnitude of the charges and the greater is the dipole moment of the bond.